Hi everyone, welcome back to this next season of the ZX Calculus seminar. Today we have Tobias Fischbach, who will be talking to us about his review on quantum circuit optimization using ZX Calculus. So Tobias, if you want to get started.
Okay, thank you very much for the nice introduction. When I prepared for the talk, it was actually quite hard because I would talk a lot about the work of other people that I know I will see in this when I give this talk. So I was more thinking about, okay, how can I give a broader overview, more perspective, and actually motivate what I'm working now in the hope that I can get your support later during the discussion section. So the first thing that we need to ask ourselves, why do we even need to do quantum circuit optimization? And right now we are talking a lot about architectural restrictions. In an ideal world, we can run all these cool algorithms like quantum approximate optimization or Shor's algorithm on large systems and be very happy about it. But in reality, we are extremely resource restricted. I put here now one example from the IBM Eagle architecture there. However, this is only the superconducting architecture, and we know that there are, of course, other architectures such as photonic or trapped ion quantum computers that impose, at least on a hardware level, different challenges and different restrictions. So the question is now, if everything is great and we have our limitations, how should we proceed? I think everyone here is already very familiar with quantum circuit optimization, the quantum circuit notation, and that X calculus. So I want to focus more on the part why we want to use that X calculus for quantum circuit optimization. And for me, I come from a perspective of combinatorial optimization. And one thing that really bothered me about quantum circuit optimization is that the native gate set that we use when we create our algorithms is often this Clifford plus T gate set. However, this is not the native language of the different architectures that we are actually using. So very often different architectures use different phase gates. So theoretically, in the end, we can get to an infinite number of universal gate sets, which also means if you want to do quantum circuit optimization, we need to think about, oh, there are now infinite commutation rules that we would need to prove. And to check if a quantum circuit is actually giving us the same output after optimization as when we started with is computationally extremely expensive. And the nice thing about the X calculus is that we have a really compact system. We only have a few generators. We have some well-defined rewriting rules that preserve the semantics. And this is, on the one hand, really attractive because it's a compact system that we play with. However, on the other hand, that X calculus is a non-terminating rewriting system. So this means some rules we can always apply. And the art, so to speak, is to know when to apply what rewriting rule and especially when to stop. So on the one hand, that X calculus that is really cool because we can express every quantum circuit as a ZX diagram. However, the reverse is not true and is known as a circuit extraction problem. And now the thing that I am really focused on is the idea of how can we now take these semantic preserving rewriting rules of the X calculus and chain them together. So just take a very abstract, high-level look about what it looks like. So in general, when we want to do quantum circuit optimization with the X calculus, it's 3 stages. First, we want to have a quantum circuit, convert it to a ZX diagram. Then we perform some algorithm on it. I do combinatorial optimization, so I'm more thinking about search-based algorithms. And then afterwards, we need to extract our ZX diagram to a quantum circuit again. And this actually gives us two different target points where quantum circuit optimization can happen. On the one hand, it can happen at the search stage, which means if we want, for example, to optimize the T-gates, or at the extraction stage, for example, when we try to aim to reduce the 2-qubit count or to be architecture aware. Also, there are now methodologies, optimization strategies, where you try to optimize, for example, the edge count at the ZX diagram level with the goal to, in the end, optimize the 2-qubit count during circuit extraction. So, in the beginning, let's focus on the search stage of this optimization pipeline. When I want to introduce the methodology, I just want to quickly define what, from my perspective, a ZX-based quantum circuit optimization algorithm looks like. So on the one hand, we have our set of quantum circuits, and we have some metric function opt that maps our quantum circuit to some type of metric. And then we define that a linear map of qubits, and we define a function gamma that then maps the quantum circuit to its linear map of qubits. And we say a function preserves its semantics if they implement the same linear map of qubits. And an optimization function f in the end is a function that on the one hand minimizes a quantum circuit metric, but also preserves its semantics. Also, we need to have a function that converts our quantum circuit to a ZX diagram. We call it here alpha. And then, on the other hand, we also need an extract function. This extract function, you see, we map the special symbol to it in addition to just a set of quantum circuits. That's the reason that, as I recall later, not every ZX diagram actually is an extractable quantum circuit. And in the end, we have rewriting rules, which are just functions that map a ZX diagram again to a ZX diagram, which changes the ZX diagram itself without changing the semantics. And in the end, the idea is that we change these rewriting rules together on a converted quantum circuit, and this gives us then a finite sequence where in the end we get an optimized ZX diagram. And in the end, a solution is from all the set of finite ZX diagrams that we have, then the subset where a certain metric that we have is minimized. Well, and of course, if the solution is optimal, it means there is no other ZX diagram that is better on that metric from all the solutions found. So now I just want to recall a little bit on the circuit extraction part of this whole optimization pipeline, because this is actually quite interesting. Circuit extraction is not just a mere conversion. I mean, we can take just our table with quantum gates and ZX spiders and just plug them in and can convert everything. However, if we think about the reverse, it's actually the assertion of causality. And when we think about it, a quantum circuit has a clear execution order of the quantum gates. So we have a clear flow of time. However, if you look at a ZX diagram, it's not that obvious to introduce like some order there. and therefore circuit extraction is needed, which is in general p-hard. And the whole idea is that these ZX diagrams that are extractable are in this MBQC measurement pattern form, which just means that we need to find a measurement sequence in our ZX diagram that does not disturb already measured qubits. So we only start to correct in this framework on future unmeasured qubits. And this is only possible if either causal flow or general flow is exhibited. And I think the standard algorithm is from Buckens et al., which is basically a 4-step algorithm where you either try to extract an easy spider, meaning which is a frontier spider only connected to one unextracted spider, or you try to extract controlled Z gates, or, and this is the cool part, you get to a frontier by adjacency matrix where when you cool. Thank you. Where you then solve the by-adjacency matrix, where the row additions correspond to the addition of CNOT gates that change the by-adjacency while removing an unexpected Hadamard wire between the target and control qubit. So much for the high-level context. Why I actually, or what I actually started out to create the survey, and what a little bit the selection criteria are. So I looked at every work until September 2025, and I selected basically on 2 criteria. First, are we using that X diagram rewriting to perform that X-based quantum circuit optimization, or are we working on the circuit extraction itself to improve the circuit extraction? And in the end, I went through and had 3 categories. On the one hand, I just differentiate, are we architecture independent or are we architecture aware? And as you see, it's roughly half and half. 14 works were architecture independent, 12 works architecture dependent. And in the next step, I then looked at the actual optimization algorithms. And afterwards, I differentiated them even more into their respective target metrics. I know the table is a little bit small, and just looking at the table doesn't give you much information. And I also think just looking at the table without proper explanations in text doesn't give you any extra value or take-home message. So I grouped for the talk the categories a little bit more up, and now sorted a little bit by grouping ad hoc and template matching algorithms together. I grouped heuristic and greedy algorithms together. Then I created a group for all search-based optimization algorithms, which means integer linear programming, tree search, look-ahead search, then this heuristic solver. Also, I grouped stochastic algorithms together, which means in this case, we are looking at genetic algorithms, simulated annealing, and a random rule selection that we found in some works. Lastly, I excluded reinforcement learning as an extra category because I would like to talk a little bit about it later on. This is why I separated it. If you now look at the graph, you will realize, oh, if you add every dot together, it's not coming up to 26. It's actually much more. Why? So the reason is that some optimization strategies are actually a combination of multiple strategies. So instead of trying to restrict a work to one optimization strategy in that context, I decided to put each algorithm that they used or optimization strategy in there separately. So, for example, when you look at the qubit count, where we appear with multiple algorithms, this is actually just one work. And overall, what you see here is that we have a cluster at ad hoc algorithms, and we start to go a little bit towards stochastic and search-based algorithms. And this is actually about time development. In the beginning, most algorithms were more ad hoc based or searching for a heuristic. And later on, in the last 3 to 4 years, the researchers started to look into more broadly into search-based methods and stochastic methods. I think you also see a little bit, for example, we only have like one work targeting that X diagram vertex count. We have some work now that target the edge count, and they are actually targeting the edge count with the idea to optimize the 2-qubit count, as we see later. So one thing I find interesting, I think there are 4 important or larger trends that we see appearing in the works. The first thing is that not just we have this idea, we are now trying to get more of this large ZX state space covered by using search-based algorithms, but also that we try to bridge the gap towards architecture-aware optimization. And I think this is really, really interesting because we have now, for example, photonic quantum computing, neutral atom quantum computing, or trapped ion quantum computing that didn't have any works early on in the field of architecture that or quantum circuit optimization. And now in recent years, we see a ramp up in these areas. And it's not just restricted now to superconducting quantum computing, which I think is also a little bit the overall trend. Because if I would need to bet on a company making scalable quantum computing, it wouldn't be a company with superconducting architectures, just because with all the fundamental noise you will always need to deal with. And especially with the idea that photonic quantum computing can be run at room temperature. However, it also means that X calculus is uniquely positioned as an intermediate representation. And if we think about compilation frameworks like TQEC, they are actually already using that X calculus. However, I just went over a recent work where they tried to find an intermediate representation with LLVM IR, so they can in the end use this for Microsoft introduced quantum IR. And I think this is also a field or a part where that X calculus can actually be incorporated in the future, because it's uniquely positioned as the idea is architecture independent, but the optimization algorithms that we use in the end can use this framework to make it architecture aware.
Sorry, Tobias.
The other thing,
I believe there's I see a raised hand in the chat, so I think someone wants to ask a question.
Sure.
Hi. I want to ask, like, maybe it's like two separate questions. Like, do you not agree that the photonic quantum computing game is very, very different from the circuit level optimizations?
I agree.
It seems like a lot of the circuit extraction is generally not needed, right? So what are the advances that you're sort of envisaging? Like so what, like, yeah, I'm not saying that it's not useful, but it's what are the use, like what, in what sense is it more useful?
I think so. If I understood you correctly, you basically ask me if, I mean, in photonic quantum computing, you don't really need to do circuit extraction because it's a measurement graph, basically. Correct?
Sure, or some variants of it, like.
Okay. I think the advantage is that right now we don't know what architecture will be in the end dominant. In the lingua franca is still the having a quantum circuit. So while I wouldn't, while I don't see the problem now with circuit extraction with photonic quantum computing, I still see the application of that X calculus there as this intermediate representation, because normally you start out with a quantum program in the form of a quantum circuit. Like maybe this changes when this Microsoft Quantum IR and find another type of abstraction to it, but fundamentally it will be still a quantum circuit that we start out with, right?
Sure, but okay, sure. Yeah, thank you.
Okay. Are there other questions? Okay, then I continue. So the next thing that I thought that was kind of cool, I think in 2023, Staudacher introduced a first heuristic to reduce the edge count that also reduced the two qubit gate count. And then Holker later improved it by using only causal flow preserving rewriting rules, and got like an even better reductions in the edge count and two qubit gate count. And then this concept was directly used by Matic et al., which combined tree search with a reinforcement learning heuristic, basically replacing the heuristic and the tree search with a reinforcement learning model based on these causal flow preserving rewriting rules in this heuristic. I thought this was kind of cool because you could really see the development of this idea in real time. And the last thing, oh God, yes, the last thing. So the last thing is actually, so during the standard circuit extraction algorithm, there is this idea that, okay, we run, for example, Gaussian elimination to solve this by adjacency matrix, and every row operation adds a CNOT gate, and then we hope that gate cancellation and gate commutation in the end gets rid of a lot of these two qubit gates added. And then there are like, there's already works where you can restrict, for example, what row operations you allow by mimicking or restricting this gate placement based on the connectivity of the architecture. Or there is also a work of Viloria, where she basically created an ILP for trapped ion computers to solve this by adjacency matrix as an idea to maximize the global gate usage, or that maximize all this, that all the CNOTs would fit in a global gate. Which also I think is really interesting because maybe we are able to find a way where we can make this step of circuit extraction better and architecture aware overall, So if we feed our result into a transpilation pipeline, maybe there is a step, for example, the routing step, that we can skip later on. Overall, there are, I think, 4 major challenges that are involved with ZX-based quantum circuit optimization. The first one is scalability. While it's such an okay. Because scalability is still a major issue. In the end, it's a non-terminating rewriting system, and we have just limited resources. So on the one hand, we need to find some heuristics, we need to find some pruning conditions that solve this issue, because even if we would now just parallelize our search, we are still not solving the fundamental issues. And finding good restrictions on our search space would actually also allow us to go towards other techniques such as dynamic programming. The other thing I saw, that there is not a real multi-objective optimization approach. Like in general, you run full reduce and then you find some cool method to optimize your edge count, your 2-qubit gate count, or you run full reduce and then you do some cool things with your Turing circuit extraction. But a truly multi-objective approach where multiple metrics are balanced is not, I didn't see. And the interesting thing about this is actually there is a genetic algorithm approach by Evan et al., where he tried to reduce the 2-qubit gate count, and he found out that basically as soon as the closer he got to beating the state of the art, the worse his results were on other metrics. So I think this might be a good hint for a multi-objective optimization approach, where we don't try to find the optimal result for one metric, but by balancing multiple metrics, we get an overall circuit that hopefully allows us to execute a quantum program earlier and on restricted or resource-limited architectures. The next thing is circuit extraction. One thing that I was surprised is that we have, for example, this result that circuit extraction is p-hard. But I didn't see the idea of using combinatorial optimization all at once on one large ZX diagram without doing the normal polynomial time algorithm. I think it's because this might be called circuit synthesis. But this is actually something I'm thinking about a lot right now. If there is a way to make, for example, one large ILP that captures a complete unitary of a ZX diagram and then creates a circuit out of it, and where the different constraints are not just the gates, but would then also allow us to bridge the gap towards other architectures. And in general, I think architecture awareness is a recent trend that we saw, and where I also think that a lot of work will be done, just because trapped ion architectures, I think, only have 2 publications or something like that. So just by the number of publications we have for certain architectures, that there will be more optimization strategies coming. One thing that you see there is that I put a reinforcement learning extra. And I think this is interesting because I see reinforcement learning as, while a very computationally expensive heuristic, it's an upfront cost. So the idea of reinforcement learning to create a model or a surrogate model that would allow us to test other optimization strategies, or in general alleviate the load long term, I think is really interesting, just because we are still having a lot of problems with classical limitations. Otherwise, we would need a quantum computer just to do quantum circuit optimization, just based on the system size that we are dealing with. However, this is unfortunate. Okay. Apparently I made a LaTeX mistake. So the main question that I had, or that arose during when I wrote the survey, was, how do the algorithms actually perform? It's really hard to compare the different works because not all the benchmark quantum circuits or benchmark diagrams are the same. Sometimes the random circuits are not well documented or provided, so it's really hard, even without executing the algorithm, just by reading the papers, to actually understand what is the best algorithm, what is a good algorithm, and also in what combination of optimizer or extractor are actually beneficial. And this brings me actually to the main reason why I wanted to give this talk, because I would like to have your feedback. In the recent months, I was working on a benchmarking framework, and the code, I put a QR code there so we can just scan it, is on GitLab, and the whole idea was, okay, I want to have a benchmarking framework that is declarative in the sense that I write a configuration file, I set an experimental parameters that are the same for every optimization I would perform, and I would like to decouple the optimizer from the extractor so that you can also test different combinations of extractors and optimization algorithm. Also, I would like to run my benchmark set or my benchmark on multiple data sets. So not just on the standard quantum benchmark set, but also on a different set of random circuits. I wanted it to be easy to use so that you can just use the CLI, or that you have like a very simple Python API. But most importantly, I wanted to share in the long run the results so that actually the community has an overview of the different methods and doesn't need to run the benchmark for every algorithm they want to check out themselves, but can just look at standard data sets and just run their optimizers and compare to them. But also, and this comes now to the a little bit tougher technological part, I didn't want to re-implement the algorithms. But you notice with the quick pace that PyZX is actually developed, a lot of works from 2 or 3 years ago is not executable because the, for example, the graph system changed, the rewriting system changed, which makes it a hell to maintain. So what is already implemented, what is there, what's going on. So right now we have JSON files to configure experiments, and the JSON files are such that they are actually mimicking the Python API. So basically, if you add optimizer parameters, they are just KW args that are passed into the optimization function. Of course, you have LaTeX output, but you also have HTML output. I have from one of my paper an example benchmark analysis ran, and I put it also on the GitLab. Like when you scan the QR code, you will come to the website, but I also put an image of like one of these tables there. So it's basically a performance, an absolute performance on different target metrics, but also you can make it already as in reference to a target algorithm, so that you're only looking at relative performance. I added like the standard quasar benchmark sets. I generated random circuits for different universal gate sets, and with the help of Fabio, we also implemented some optimizers already. So just to show you how the compatibility and how the integration would work. In the end, on the right, you just see this JSON file, right? I mean, it's pretty simple. You have global experiment parameters. You have then the actual instance setup. You can define multiple solvers with multiple parameters. You can add metadata for the different solvers. You have different extractors that you can use. And in the end, the instances are created for all solver and extractor combinations. And if I just show the command line version. So if you look at the example folder, you can just then do like an experiment -c and then run the config.json, or just directly execute the Python config.py and then add your config.json there. Now we come to the part how we worked on the compatibility with legacy code. I am actually not happy with that, but I didn't know any way without starting to overcomplicating dependencies by shipping containerized versions of PyZX, and that is just for that specific optimizers. So in the end, if your optimizer works with current upstream PyZX, it just, you write a wrapping, there's a wrapping function, it takes a base graph, it takes optimizer functions, optimizer parameters that are exactly as the ones upstream, and then you just execute your optimizer and return the graph. However, the fun starts as soon as incompatible PyZX versions are involved. And for this, we actually, in the end, decided to distribute the optimizer with a stripped-down version of the PyZX dependencies of the version the optimizer was published with. So as long as Python doesn't undergo major changes, we basically convert the current graph or current graph data type of PyZX into a legacy ZX diagram, and then just keep the original optimizer untouched. It just imports the legacy PyZX functionality it needs directly as part of the module. It's not ideal, but we didn't know how we would do it differently without creating a maintenance hell. If you have any better ideas, we are of course very happy to change that. That's why I also would like to have your feedback about that. In the next few months, the whole idea is to especially start to automate it. So meaning if a new optimizer is added, we just run the benchmark with a GitLab runner. We update then a website with all the optimizers. And afterwards, we also regularly want to check, does upstream PyZX break any of the optimizers that doesn't ship with compatibility to some legacy version of PyZX, and if so, that we get a notification so we fix that. And overall, it's also a really big question about how we can integrate our framework actually with other frameworks. So it's not just about automation, but in the end, what is the easiest way for you when you run a benchmark or an end-to-end pipeline that you can put it directly into your research. Also, I would like to ask you later on, is there like advanced functionality, advanced metrics, or some experiments that you want to like? But especially, please test, please give feedback so we can make this a proper tool for the community. Lastly, I would like to put out some discussion points before I end. So, are you even interested in this tool? If so, would you be so kind and write a pull request with your specific optimizer? And also, are you interested in other things like computational efficiency or circuit size versus solution quality, for example, in under constrained runtime conditions? Is there something how we can make this a fair comparison? Because right now I generated some random circuits. I have some, we have the quantum benchmark circuits, but I saw that on some preliminary tests that the type of benchmark set or data set that you use heavily impacts actually the result of your optimizer or of your extraction algorithm. So what is actually a fair data set that we can use that is not too large, so it's computationally feasible, that actually fairly represents the advantages and disadvantages of the different optimization strategies. Also, is there something that when you see it, you just say outright, oh no, I don't want to use this tool ever, like not at all? So with this, I basically can end. My PhD ends soon, so if you would like to discuss with me later on or longer about it, I'm looking for a postdoc. And you find my website, my CV, my email address. It's listed there. Also the survey and the code as the resources on the right. And this is it. Thank you for your attention, and I'm happy to discuss with you.
Right. Thanks very much, Tobias, for the very nice talk and all the work you've done trying to get all these different methods to talk to each other and be comparable. Do we have questions or comments from the audience? Leah?
Hello, thank you very much for the talk and just very comprehensive overview. There's a lot of literature to get through. I'd like to ask about if you had to look at comparing with circuit-based optimizers. Did you find anything interesting or some general comments that you found if you did any comparison of that sort, or if combining with circuit-based optimizers? Specifically, the completeness result for quantum circuit completeness.
What is exactly your question?
Were you able to scope out how comparison, how CX diagrams optimization versus quantum circuit optimization approaches were you able to benchmark those as well? But just
no, I didn't do that. So right now, like from the benchmark itself, it's only a very small subset of optimizers. So for me, now doing any general statement about that would be just speculating.
Okay, thank you. I wanted to also ask if people know if there's been quantum circuit optimization work done with the complete quantum gate set for qubits. So I'll send it in the link in the chat, but it's a paper from recent years, well, 2 years ago, but I wonder, I don't know if there's any quantum circuit optimization that has been done with these rules, and I'm just curious if someone has attempted it. Thank you very much for the talk.
Okay, Kay, you also have your hand raised. Do you want to ask a question?
Hi. I'm sorry. Like just now, I guess I asked a question about photonic quantum computing. I think I'm also just curious in what is the state of the art in at least in the ZX world right now, and what are you really optimizing over? Because the game is very, very different if you're looking at measurement based, fusion based, or whatever Xanadu is doing, like somewhere in between with these CV based stuff. I'm just curious, like what is the state of the art in terms of what to optimize over? Because you're not really counting 2-qubit gates, are you? It's like it's a very different game. Sorry, maybe that's really what I was trying to get at.
Yes.
I don't know I'm not
Mhm.
I don't know what it is. I'm really genuinely curious about what's the state of the art.
I think there is one work from Silk who was working on photonic quantum computing, and I think I saw a second work late after I already submitted the survey. So I didn't put it in there, and I don't remember that clearly. But I think it was in general about optimizing the measurement graph. I am not remembering that clearly because this was a lot of work. But I can look it up again. I think at most there are 2 works in the ZX world working on photonic quantum computing.
Okay, thank you. Yeah, thank you.
You see? No, don't think so.
Okay.
Mr. Koehler.
Hi, thank you for the talk. So I just want to follow up a bit, also based upon Leah's feedback. So Leah, are you asking how effective it is to use the automated tool to apply rewrite rules to simplify quantum circuits? Was that what you were asking earlier?
Not quite. I guess I was just asking because with this benchmark suite for ZX diagrams, then you can compare a host of different ZX optimizations with existing quantum circuit optimizations. So the ones kinds that don't go to a graph form and then extract. Or other methods like tensor network or other kinds of methods. And so I was just curious if that's been tried yet. Just any preliminary results. I was just fishing for that. But that would be much more possible now that it's all collected nicely. So I recognize it takes so much work to put it all together, and I really appreciate that.
So right now it's basically everything that gives them. So I basically put it in there that you either need to start out with a ZX diagram or with a quantum quantum circuit. And then there is a function that converts it to a PyZX graph. And I only put ZX or optimizers in there that are based on PyZX. So I guess you can also extend that to other optimizers, but then you would basically need to add add the instance constructor class that it actually selects the optimizer function and the data structures based on the specific framework that you want to use. So if you look at the data structure itself, for example, the result JSON, it's basically the exact metrics, how they appear in the PyZX framework, just that I add like an original or an opt when I flatten the results into tables. But I try to stay as close as possible to the upstream PyZX with the idea that people can use it easily and are familiar and don't need to guess too much about what my personal preferences are. But I think you can extend it. But in general, I think I'm happy about everyone who contributes, does bug testing, or makes it, in general, a really good work that we can compare our optimizers. Because I think this is actually one of the problems that we have in this idea, in that express quantum circuit optimization, and that it's really hard to compare the different optimizers and extractors on a comparable benchmark set.
That's great. Thank you.
I have a question related to this. Like, when you are thinking about this targeted metrics, is the resource overhead the only thing that you're worried about? Do you also worried about the success rate of getting the expected outcome after the computation?
So
because
right now,
a circuit very short, or like if you have two circuits that have different resource overhead in terms of different metrics, and then you run, like they both represent the same linear map, but then they may have different reliability in terms in the execution, right?
So right now, it's purely this high-level metric. So we are not considering any architecture awareness or any reliability. It's literally, okay, you have an optimizer, you run it, you get the 2-qubit count, the T-gate count, the number of gates, the circuit depth. You can look at the extracted and unextracted that X diagram based on what the individual optimizer gets you. When I have more optimizers there, and I can and we decided, and I also want to do like a Discord discussion about that, about exactly what is a fair benchmark set. So I will then run on our cluster all the optimizers on a defined set of quantum circuits, so we can actually have a better overlook. But of course, if you are interested in certain other metrics, we can extend that. That's not the problem, right? Right now, it's just this really plain idea of, okay, T gates, edge count, circuit depth, 2-qubit gates.
Okay, Michelle, you want to ask the question?
Yeah, if I can, and if I am not taking the time of everybody, but otherwise, thank you very much for the talk. Very, very insightful. I'm new from the crowd, so I'm cultivating myself, but I'm asking, you try always to extract circuits which are reduced to local measurement and to qubit gates, right? So at the very end of the story. I got it right, yeah. And did everybody ever thought seriously about the fact, because, you know, when I simplify circuits, the few that I've simplified with ZX, you very, very rapidly end up with these multi-qubit spiders and so on. And, you know, there are platforms which are intrinsically long range, like IonQ or disrupt ions. And did anybody ever thought seriously about taking this ZX aspiration out to build multi-qubit gates that could just work one super complicated, interesting option just to accelerate the circuit in one shot? I don't know if I make myself clear, but
So if I understand you correctly, you ask about is there other people trying to, for example, take advantage of multi-qubit gates, or for example, an all-to-all connectivity or something like that.
Yeah, the DEX gets very, very rapidly multi-qubit, right? You get these multi-edge spiders that come out, and this could be implemented physically in principle, right? So with a multi-qubit gate, right? And did anybody thought seriously about this? And
I think Viloria did something like that by trying to use global rotation or global gates on trapped ion quantum computers. But this was during the stage of circuit extraction. It was not during just the ZX diagram optimization.
I see. Thanks.
Arielle?
Yes. Let me comment on that one last question for a second, which is that like not every multi-qubit spider is necessarily a gate that you can do on an all-to-all connected device. So you run into some issues there, but I think also John had a paper where you used some all-to-all like gadget where you used that for decomposition, like very long time ago. But my real question had to do with the comparability of the different algorithms that are in there, because I feel like everything uses that X calculus as a description for what your algorithm does, but then within that we might use different, like almost like normal forms. So you assume that you're the algorithm explains like you have a circuit, I can get it into this ZX diagram form that has these properties, and therefore I can use this algorithm to extract it. But then another algorithm is like, well, I like to use a different form, and then I get some things. Some things are easier, some things are harder, and but now I'm using that form, and then that kind of makes the algorithms harder to compare, because there is no transformation from like the one ZX diagram form to a different ZX diagram form, where these algorithms are like relying on. They all come from a circuit and then go to a circuit. Yeah, could you like, is that also like your experience with like trying to mix and match these algorithms?
I took the lazy way out. I only currently implemented algorithms where I didn't need to ask myself that question.
No, exactly.
So I'm aware of that problem, especially, for example, there is a work where they use template matching, and they prove the different templates using that X calculus that they are correct. And they are only restricted themselves to implementations of, I think, hydrogen or some other small molecules to represent on a quantum computer. So I think if in the end it's like just a category, right? And if we see that certain algorithms are not executable or not, well, executable is the wrong word. If it's not correct to run an optimizer on with a certain ZX diagrams, because it's just mathematically incorrect at that point, of course we cannot run it, right? But this would then mean we would need to open an extra category for that. Which I think doesn't really matter, because for me an extra category is just another folder in my benchmark circuits or benchmark diagram folder that I can just import with my interface. Like from a technological standpoint, just making another category, it doesn't really matter. For the analysis, I just then give it another name and say it should pull the category or this data from another folder, and that's it. So, of course, if we design such a benchmark, we need to take this into account.
Yeah, or at least then you can get some numbers out, but then they won't be comparable with other methods. Like very concrete example is that the normal ZX diagram extraction like only assumes like G flow or polyflow. But then my algorithms, for example, they tend to have this like very strong Hamiltonian form that I'm just using ZX calculus to quickly prove things and reason about it, but not much. Those algorithms don't work nicely on arbitrary ZX diagrams. Only that ZX diagrams are a very particular structure. But
I can only say, send me a pull request.
Yes.
Tell me what you think is a fair representation of your
Yes.
circuits, and we just have another category then.
No, exactly. Now I will make one when my library is ready. Yes.
Tobias, I wanted to ask, because I think at some point you mentioned that like circuit extraction is Sharpie hard, so you can surprise people that haven't sort of used Sharpie complete problems, like maybe Sharpie problems, to consider the circuit extraction problem and do it that way. And I think you mentioned the ILP approach to this.
Yeah.
I wanted to make like a point where in our paper we prove it Sharpie hard, but the upper bound we find, I think, is NP using a Sharpie oracle. And I think that might be sort of the actual bound. So then I would be surprised if you could solve the general circuit extraction problem using just a Sharpie complete problem. Like I would assume you need something even stronger than that. But yeah, I'm not entirely sure if that works. But yeah, if you could show that that works, then you would show that circuit extraction is in Sharpie, which is also would be a very nice result.